Welcome to the second lecture on real analysis. So here we will discuss how to generate sigma algebras from the so-called open sets. And these open sets are elements of topological spaces. So those who are not familiar with topological spaces, let us consider the following definition. So a collection T subsets of X will be called a topology on the set X if the following three properties are satisfied. So T1 means that the empty set and the set X are elements of T. The second condition is that it is closed under arbitrary unions. So meaning if I have a collection of sets in T that are indexed by this set I, this set I can be countable or uncountable. Then the union of this collection must be also in T. And finally, it must be closed under finite intersections. So if you take two elements in T, then the intersection must be also in T. And of course, by induction, T sub 3 can be extended to any finite number of elements in the collection T. So if your collection satisfies these three properties, then we call it a topology on X. And the pair X with the topology T on X will be called a topological space. Now, if the topology T is clear in the context, or we know that there's a topology defined on X, then we simply refer to X as the topological space for simplicity. The elements of a topology are called open sets, and the collection T complement, by definition, this is the collection of all complements of elements in T are called the closed sets. So therefore, the complement of an open set is a closed set, and vice versa, the complement of a closed set is an open set. Okay. So now there's what we call a Borel sigma algebra on a set X, or on a topological space X with topology T. This is basically the sigma algebra generated by the open sets. So recall that the sigma algebra generated by some collection is defined to be the smallest sigma algebra containing that collection. And it can be obtained by taking the intersection of all sigma algebras containing the topology T. So this is the definition of the sigma algebra generated by some collection we have defined in the previous lecture. So first observation, of course, the Borel sigma algebra, which we here denote by B of X, can be also generated by the closed sets. This follows immediately from the definition because the complement of an open set is a closed set, and we know that the sigma algebra is closed under complementation. Okay, the next one. So here we need some concepts in topology. Okay, so consider a sigma compact topological space X. In other words, there's a sequence of compact sets K sub n such that the union of these compact sets is X. So in other words, we can divide the topological space X into a countable union of compact sets. So recall, what do we mean by a compact set? So a subset K, so let's have a note here. So a subset K of a topological space X is said to be compact if for every open covering, and that means that for any collection of open sets, okay, that covers K. So K is contained in the union of these open sets, then there must be a finite subset, say F, of I, to which if we take the union of the open sets O sub I, where I is the finite index at F, this is still covers the compact set K. Put in another way, so if every open covering of K can be reduced to a finite subcover. So that is what we mean by a compact set. Okay, so that's the first condition. The second condition is that it is Hausdorff. So in other words, you pick two distinct points in X, okay? You can find two open sets U and V, wherein U contains X, V contains Y, and they are disjoint. So it is illustrated here in this picture, wherein you have two distinct points X and Y. Then you should find an open sets, two open sets that will separate them, meaning U contains X, V contains Y, and they have no point in common. So again, let us suppose that our topological space is sigma compact and it is Hausdorff. Okay, denoting by K, the collection of all compact sets in X. Then with the above assumptions, the Borel sigma algebra on X can be also generated by the compact sets. Okay, so the proof is as follows. In Hausdorff spaces, we know that compact sets are closed, so therefore the collection of compact sets is contained in the complement of the topology, meaning the collection of all closed sets. Since there are more elements in the collection of closed sets than the compact sets, then this implies immediately by the definition of the sigma algebra generated by a collection, the sigma algebra generated by the closed sets contains the sigma algebra generated by the compact sets. Okay, and recall that from the first remark, this is the same as the Borel sigma algebra on X. Okay, so here we now have the inclusion that the Borel, or the other way around, that the sigma algebra generated by the compact set is contained in the Borel sigma algebra. Okay, so to prove the other inclusion, so suppose that C is an element of the complement of the topology. In other words, C is closed. Then I can write this C as C intersection X. Take note that X is the a universal set, meaning C is a subset of X here. And by assumption, X is sigma compact. So X is the union of the compact sets K sub n. And by the distributive property of the set union over intersection, we have this equality here. Okay. Now, we know that this is a subset In fact, it is a closed subset of the compact set Kn. Okay. Since C is closed and compact sets are closed, C and Kn are closed. Therefore, the intersection is also closed. And in this case, we know that closed subsets of compact sets are closed. Or I should say compact. So this means that this intersection is in the collection of the set of all compact sets. Okay. Hence, it would be in the sigma algebra generated by the compact sets because the sigma algebra is closed under countable unions. Okay. So what we have shown here is that if I started with an element in the complement of the topology, then I have shown that it is also an element of the sigma algebra generated by the compact sets. In other words, the complement of the topology is contained or a subset of sigma of K. Okay. Sigma of K, therefore, is a sigma algebra containing the closed sets. Since this is the smallest sigma algebra that contains the closed sets, this implies that the sigma algebra generated by the closed sets is contained in the sigma algebra generated by the compact sets in virtue of this inclusion here. Okay. So combining these two inclusions, we conclude that the sigma algebra generated by the closed set is the same as the sigma algebra generated by the compact sets. And we know that this one is equal to the Borel set of X according to our first remark here. Okay. So again, to summarize, if you have a sigma compact Hausdorff topological space, then the Borel sigma algebra on X can be generated also by the compact sets. Okay, by the way, I should also say that elements of the Borel sigma algebra are called Borel sets. So elements of Bx are called Borel sets. Okay. And finally, we have the following observation. So if we have a collection C of open sets in such a way that every open set in T can be written as a countable union of elements in the collection. Okay. And there's a correction here. This should be a subset. Okay. So again, if we have a collection C in such a way that every open set can be written as a countable union of elements in C, then we can generate the Borel sigma algebra on X by this collection C. Okay, so the proof is simple. Of course, based on the assumption here, which is this one, since C is contained in T, then the sigma algebra generated by C is contained also in the sigma algebra generated by the open sets. So now we have the inclusion. First inclusion. Take note that by definition, this is the Borel sigma algebra on X. Okay, so for the second one, take note that based on the assumption, any open set can be written as a countable union of elements in C. Since a sigma algebra is closed under countable unions, and the sigma algebra generated by C contains C. Therefore, this countable union here is an element of sigma of C. Hence, T is a subset of the sigma algebra generated by C. And this is what we have written here. Therefore, sigma of C is a sigma algebra containing the topology T. And since sigma of T is the smallest sigma algebra containing T, this implies that sigma of T must be a subset of sigma of C. Okay. Hence, combining these two inclusions here, we conclude that the sigma algebra generated by C is the same as the sigma algebra generated by the open sets. And recall again that this is the Borel sigma algebra on X, proving this equality here. Okay, so these three theorems give us alternative collections where we can generate the Borel sets on a topological space X. So as a quick example, so in the Euclidean space Rn, under its usual topology, according to the previous theorem, okay, or first by definition, the Borel sigma algebra in Rn is generated by the open sets. This is by definition. And since sigma algebra is closed under complementation, it can be also generated by the closed sets. And we know that Rn is Hausdorff. Well, to do that, to show that it is Hausdorff, if you have two distinct vectors, x and y, say, you just choose open balls, let's say with radius r and s, that contains x and y, and they are disjoint. So Rn is Hausdorff. It is also sigma compact. To show that it is a sigma compact, it is enough to choose a Kn to be the closed ball centered, let's say, at the origin, having radius n. And this is the set of all vectors in Rn with a Euclidean norm less than or equal to n. So this is compact since it is closed and bounded. And we know from the Heine-Borel theorem that compact sets in Rn are precisely those that are bounded and closed. So this is closed, this is bounded, hence compact. And you can see immediately that if you take the union of the k sub n's for n from 1 to infinity, you get the Euclidean space, Rn. So therefore, from the second remark that we have established a while ago, the Borel sigma algebra on Rn can be also generated by the compact sets, which we denote here by k to the n. Okay, so let us consider other generators of the Borel sigma algebra on Rn. So for this, let us first define what do we mean by two vectors with this order relation, less than. So consider two vectors A and B having components A1 up to AN and B1 up to Bn respectively. So in this case, the A sub case and the B sub case are real numbers for k from 1 to up to n. Okay, then we write that A is less than B if and only if the corresponding components satisfy that relation. In other words, if A sub k is less than B sub k for every index k from 1 to n. Okay, so similar definitions will be applied to the other order relations. So for instance, this relation here. So we say that A is less than or equal to B if and only if the corresponding components satisfy the same inequality. So meaning if A sub k is less than or equal to B sub k for all indices k, then we write A less than or equal to B. So with this notation, we can now define more compactly what we call the open cells. So the open cell AB, okay, is the set of all x in Rn which are between A and B, meaning A is less than x and x is less than B. Since these are vectors, the order relation here should be understood in this sense. Okay. Of course, one could immediately show that this is the Cartesian product of open intervals. And these intervals are namely the intervals corresponding to the components of the vectors A and B. Okay, so what are the open cells in R? These are basically the open intervals. What are the open cells in R2? These are the open rectangles. Okay. And in 3 dimensions, you could imagine that these are the open prisms. So in 3D, you should think of inside the box, so without the surface area. Okay, so those are open cells in Rn. Then we have the following theorem. So denoting by I sub 0 raised to n, okay, to be the collection of all open cells in Rn. So n here refers to the dimension. The subscript O here refers to the open cells. Okay. Then the Borel sigma algebra on Rn with its usual topology is equal to the sigma algebra generated by the open cells. Okay, so the proof here is only one line. You apply 3 and the Lindelof theorem. Okay, so let us recall what is part 3. This statement here, okay, wherein in the current situation, C is the collection of open cells. Okay. Then we would like to ask if every open set in Rn can be written as a countable union of open cells. And in fact, this is what we call Lindelof theorem. This is a special case of Lindelof's theorem in topological spaces, but let us state the specific case of Rn. So the theorem states that every open set in Rn is the countable union of open cells. Okay. And in fact, we can add more. With rational endpoints. So by endpoints, we mean this A and B here. So the components of the endpoints must be rational numbers. So the proof is given in the lecture notes, but let us discuss the main idea of the proof with this picture. Okay. So consider an open set O. Okay, and pick a point X in the open set O. Since X is open, by the definition of an open set in Rn, this implies that we can find a ball, okay, containing X, and more precisely, X having the center. Okay. In this ball, you need to look for an open set containing X and lies entirely in the open ball. Okay. So in the case of the two-dimensional Euclidean space, you will have a rectangle here, or a square. There's no reason that the endpoints here are rational numbers. So what we do is we apply the density of the rationals. So you could draw the diagonal or the radius, okay? And then between two vectors, you can find another vector in between, meaning an element passing through the line segment, one from X and the other endpoint on the boundary of the unit ball or the boundary of the ball. Then, and this point here would have rational endpoints. Okay, so all of these four corners here will be a vector having, or a point in Rn having rational components. Okay, so now you have covered this particular point of X with a cell having rational endpoints. Okay, so you do that, okay, at every element of X. Okay. And one has to show that indeed by this construction, O can be written as the countable union of open cells having rational endpoints. So if you want the more precise proof, you check the lecture notes. Remark, okay. In fact, the previous theorem also holds for other cells, not only for open cells. So it holds for half open, half closed cells. Okay, and it's also valid for the closed cells. Of course, in the latter case, we need to include in the collection the empty set. So for instance, if we denote, let's say by IC n to be the set of all closed cells such that A and B is in Rn, A is less than or equal to B. And let's say we combine this with the empty set. Then the Borel sigma algebra on Rn can be generated by the closed cells, including the null set. Okay. And according to Lindelof's theorem, in fact, we can take A and B to be rational with rational components. And likewise, the Borel sigma algebra in Rn can be generated by the closed cells with rational endpoints. Okay, so the next topic will be on semirings, Dinkin systems, and monotone classes. So these are also collections of subsets of a given set, and they satisfy certain properties. We will see later how to generate rings from semirings and how to generate Dinkin systems, or how to generate sigma algebras from Dinkin systems. Okay. The significance of this is, for instance, in the case of sigma algebras, it might be difficult to prove that a collection is closed under countable unions. So one might show that it is closed with respect to a more relaxed condition. And these are the Dinkin systems that we will discuss later in the lecture. So let's start with the definition of a semiring. So a collection H of subsets of X will be called a semiring on X if we have these three properties called SR1, SR2, and SR3. So first, the empty set must be in the collection. It is closed under finite intersections, and it is closed under, or the set difference can be written as the disjoint union of elements in the collection. To be precise, if I have two elements in H, I can find a finite sequence of elements C sub k in H in such a way that I can write the set difference as the union of these sets C sub k, k from 1 to n. This does not mean that the set difference is in H. It only tells us that the set difference is the union of pairwise disjoint finite sequence in H. Okay. So the first remark. So a ring is necessarily a sigma ring. Okay. Well, to justify this, one should just simply take n to be equal to 1, and you take C1 to be A minus B itself. And recall that a ring is closed under set difference. And by De Morgan's law, if you combine that to SR2, this will imply that it is also closed under the set union. Okay. Of course, there are sigma rings that are not rings. And we will give an example later. Okay. SR3 can be generalized in the following way. So if you have, let's say, a sequence of elements in a semi-ring H, say A, B sub 1 up to B sub n, then we can find a pairwise disjoint sequence of elements in H, finite sequence of elements of H, in such a way that A minus the union of the B sub j's is the union of this pairwise disjoint collection. Okay, so let us look at the proof. So this is done by induction. So first, if n is equal to 1, then we basically have the third condition or third property of a ring SR3, semi-ring SR3. So suppose that the claim is valid for n sets. So our aim is to show that it is also valid for n plus 1 sets. So let us consider the following sets in the semi-ring H. Okay, so by the induction hypothesis, there exists a pairwise disjoint collection, meaning C sub k intersection C sub L is empty if k is not equal to L. And this equation here, which we shall call asterisk, okay, holds. Okay. Now, our aim is to write A minus the union of the sets B sub j can be also written as a finite union of pairwise disjoint elements in the semi-ring H. Well, in order to apply the induction hypothesis, we need to subtract from A the sets B sub 1, the union of the sets B sub 1 up to B sub n, and after that we subtract Bn plus 1. We did this so that we can apply this equation here. Okay, so that would be the union of the C sub k's, k from 1 to m, and applying the distributive property. This is basically C sub k minus Bn plus 1. Now, if we apply SR3, For each k from 1 to m, there exists a collection, let's say CKL, L from 1 up to m sub k. So the number of sets involved depend on k, which are elements of the sum-ring H, such that C sub KL intersection C sub Kj, if L is not equal to J, and the C sub K's would be C sub K minus Bn plus 1 would be the union from L equal to 1 up to Mk of the CKL. Okay. Now, if you put this in this equation, you will now have a finite union of pairwise disjoint elements of the sum-ring CKL. And note that CKL intersection, let's say C Rj is empty if the pair KL is not equal to the pair Rj. So if at least one of the components of the ordered pairs KL and Rj are different, then these sets C sub KL and C sub Rj are disjoint. This follows, in fact, from the fact that the C sub K's are pairwise disjoint, as well as the construction provided here. Okay, so we have written the set difference as a finite union of pairwise disjoint elements of the sum-ring, and this completes the induction step. Okay, so therefore SR3 is also valid when we take the difference, or when we replace B by the union of finite elements in the sum-ring. Okay. So let us consider two examples. The first one is that this is the set of all singletons, that is sets having only one element, and the empty set. This is clearly a sum-ring on X. SR1 is already provided here. Okay, so, and then the intersection of two singletons is either empty or the singleton itself if X is not equal to Y and if X is equal to Y respectively. So in any case, the intersection still belongs to the collection H. And finally, we have the same for the set difference. So if X is equal to Y, the set difference is in, okay, let's do that again. So if X is equal to Y, the set difference would be the empty set, and this would be X if X is not equal to Y. So in this case, we have a countable union of elements in the sum-ring. In fact, the union is the set, either the empty set or the singleton itself. Okay, so this is a summary on X. Another example, so let us consider the following set I. So the set of all half-open, half-closed intervals, okay, in the set of real numbers. Okay. Here we need to include that A and B can be the same. Okay. Similarly, we define I sub q to be the set of all half-open, half-closed intervals, or a cell having rational endpoints. And these are semi-rings on R. Okay, so first let us justify this in the case of in the case where the endpoints are real numbers. SR1. Okay. The empty set is the half open, half closed interval 0, 0. Take note by definition that is the set of all real numbers x such that x is greater than 0 but less than or equal to 0. Of course, there is no such x that will satisfy this. Hence, this cell or this interval is the empty set. Okay, so that's the first part. Okay, for the second, if we take the intersection of two cells, is it again a cell? Okay, so you can consider all cases, but let me illustrate the case where the interval AB is located in this part, and the interval CD is located in this part. This way, the intersection would be this shaded region here. And from the picture, we could see that it is also a cell. What is the left endpoint? The left endpoint would be the largest endpoint between the two. And in this illustration, it is C. And the right endpoint is the smallest between the right endpoints of the two cells. And in this illustration, it is B. Okay. And this is clearly in I. And in fact, you could show that this one is less than or equal to this quantity here. So therefore, I is closed under intersections. Well, for the third condition, let us take the difference between two cells, AB and CD. The worst case scenario here is that the cell CD lies inside the cell AB, which is illustrated in this figure here. Okay, so the interval CD lies entirely in the interval AB. And if we subtract CD from AB, we would get these two cells here. Since C is not included here, in the difference, C must be included. On the other hand, since D is included here, D must not be included in the difference. And one can write this set difference in general as follows. So for the first interval, you take the left endpoint of the larger set, and then you take the smallest between B and C. In this illustration, the smallest is C. For the other interval, the right endpoint is the same as the right endpoint of the larger cell, and the left endpoint would be the maximum between A and D. In this case, the maximum is D. So D is larger than A in this figure. Okay. So this formula will be valid in all cases, and I invite you to check all the other possible scenarios where CD is located to AB. For instance, what if this is AB and C is the same as A, but D is inside AB? So that's also the other case. And in fact, this formula will also give that one. But of course, one of these sets must be empty. In any case, we have written the set difference as a union of cells in I, and one can check that these are disjoint. Okay, so on the second example, we would like to generalize this in multi-dimensions. In other words, we would like to show that the n-dimensional analog of this example is also valid in Rn. Well, in order to do that, we need the following theorem. So if I have a sum-ring H on X and another sum-ring K on Y, then the Cartesian products of these sum-rings, which is defined as the collection of Cartesian products where the first component, A, belongs to the sum-ring H, and the second component, B, belongs to the sum-ring K. Then one can show that this is also a sum-ring on X cross Y. So therefore, the Cartesian product of two sum-rings is again a sum-ring on the Cartesian products on the underlying sets. In this case, X and Y. Okay. I will give the idea of the proof and left the technical details to you for you to write. Okay. First, we know that the empty set belongs to H and it also belongs to K because H and K are sum-rings. This implies that the empty set, which is the Cartesian product of the two empty sets, is in H cross K. And this is basically SR1. For SR2, we have the following. So take two elements, AC of H and BD of K. So in this illustration, the horizontal component would be x, and the vertical component of y will be y. So A cross B will be this rectangular region here. On the other hand, C cross D would be this rectangle here. SR2 wants us to verify that the intersection between these two rectangles is again a rectangle. Well, one can check that the intersection of these two rectangles is given by the intersection of the first components, AC. In this case, this is this region, and the intersection of the second components, BD, which is this portion here. Hence, the Cartesian product would be this shaded region here in green. Okay. Since H is a semiring, it is closed under intersection, so this must be in H. Since A and C is in H, and this must be in K, since B and D is in K. Therefore, that is the second condition, SR2, in the definition of a semiring. For SR3, we need to cleverly write the set difference of these two rectangles, A cross B and C cross D, as a union of two disjoint rectangles. Well, one way to do that, but first, if we subtract the two rectangles, meaning A cross B minus C cross D, that would be this region here in red. Okay, and we divide it in two parts. This will be the first component, and this will be the second component. The first component would be this set. So A minus C would be this segment here. B would be this segment. So A minus C cross B would be this rectangle here, region 1. The second region would be A intersection C, this line segment, and then B minus D, it should be this segment here, or I should say this segment. This is B minus D. And this is A intersection C. So the corresponding rectangle would be this part. Okay. So first, the question would be, are these two pairwise disjoint? Of course, from the figure, it is clear, but in terms of these formulas, take note here that the first component contains C, elements of C. On the other hand, on the first rectangle, the first component does not contain C. So therefore, they are pairwise disjoint. And from SR3, we could write A minus C as the union of some C sub k's, K from, let's say, 1 to M, cross B, and then the union of some pairwise disjoint collection A intersection C cross, let's say, D sub J. Okay. So here we have written A minus C as the union of the C sub K's and B minus D as the union of the D sub J's. Hence, we have written the set difference or the difference of the two rectangles as a pairwise disjoint union of rectangles in the semiring. So that's basically the idea of the proof of this theorem. So again, the Cartesian product of two semirings is again a semiring. And as usual, by a simple induction, if you have n semirings H sub j on a set X sub j, the Cartesian product of these semirings is again a semiring on the Cartesian products on the underlying sets. Okay, so recall that the Cartesian product xj here is the set of all n tuples such that x sub j is an element of the capital X sub j for all j from 1 up to n. So that's the definition of the Cartesian product of n sets. On the other hand, the Cartesian product of the semirings H sub j is the Cartesian products of the sets A sub I, or I should say A sub j. So this is the Cartesian products of the A sub j's such that A sub j is in the semiring H sub j for all j from 1 to n. And by this, it follows immediately that I to the n, or I to the n sub q, so these are the cells having rational endpoints, are semirings on R sub n. Well, this follows immediately since In, as we know, is the Cartesian product of the cells I n times. Okay, the next theorem attributed to the mathematician Han gives us an idea how to characterize the ring generated by a semiring. Well, according to this theorem, it states that the ring generated by a semiring H is the collection of all pairwise disjoint unions of elements in the semiring. To prove this theorem, so for simplicity, let us denote this collection here by R. So an old strategy, we show that one is a subset of the other and vice versa. And therefore, we have equality of the two sets. Okay. So the first inclusion can be obtained immediately as follows. So take note that the semiring is contained in the set R. Well, this follows immediately if you take n to be equal to 1. And likewise, according to the fact or to the definition that this rho sub h here contains the this ring generated by H contains H. Therefore, this union here must be also in rho sub H. Hence, R is contained in the ring generated by H. And this proves the first inclusion. Now, for the second inclusion, we claim that R is indeed a ring. And according to this inclusion, R is a ring containing H. Therefore, the ring generated by H must be a subset of the larger ring R. But as we know in the previous part, R is a subset of rho of H. Therefore, combining these two will prove that R is indeed equal to rho of H. Okay, so to prove that R is indeed a ring, we need to verify the properties according to the definition. Now, if we take A1 to be the empty set, okay, and N to be 1, then the union of the empty set is obviously empty. Then by definition of R, look at the definition here, this implies that the empty set must be in R. So in other words, we just take this collection to consist of only one element, and that element is the empty set. And we are guaranteed that the empty set lies in H since H is a semi-ring. Okay, now with respect to the set difference, okay, consider two elements A, B, and R. Okay. By the definition of R, this tells us that A can be written as a union of pairwise disjoint elements in H, which is written in this way. So A is the union of A sub k, k from 1 to n, A sub k is in H, and A sub k intersection A sub j is empty, provided that the indices k and j are different. We can also do that. So we can also write B as the pairwise disjoint union of elements B sub j in the semi-ring H. Performing the set difference, one can show that A minus B is the union of the quantity A sub k minus the union of the sets B sub j. We claim that this is indeed in R. So to verify this, okay, recall from SR3, or in fact, the induction part of SR3 that we have shown a while ago, I can write this as a union of, let's say, C sub KL, L from 1 to MK, where the C sub KLs are in H, and they are pairwise disjoint. So say KL intersection C, let's say RJ is empty if the ordered pair KL is distinct from the ordered pair RJ. Therefore, we have written A minus B as a finite union of pairwise disjoint elements in the semi-ring. Hence, A minus B is in R. Hence, R is closed under set difference. Okay. So for R3, take note that we need to prove that it is closed with respect to unions. So the idea here is the following. So if you have, let's say, two sets, A and B, then this would be A minus B, this would be B minus A, and this would be A intersection B. So therefore, we can write A union B as the union of three pairwise disjoint sets. And that is A minus B, B minus A, and A intersection B. From R2, we know that A minus B can be written as the union of pairwise disjoint elements in H. Interchanging the roles of B and A, that would also imply that B minus A can be written as a union of pairwise disjoint elements in H. On the other hand, for the intersection, you can write the intersection of A and B in this way. Okay. And we know that this is an element of H by the fact that a semi-ring is closed under finite intersections. And that would be SR2. And this is also pairwise disjoint. This comes from the fact that the A sub k's are pairwise disjoint and the B sub j's are pairwise disjoint. So in other words, A sub k intersection B sub j. If you take the intersection with, let's say, A sub r intersection B sub l, this is empty, provided that kr is distinct from rl. Hence, we have written the intersection of A and B as a pairwise disjoint union of elements in the semi-ring as well. So therefore, if you combine all of those observations, this union here can be written as a union of pairwise disjoint elements of the semi-ring H. And by definition of R, this means that the union is also in R. If you go back with the definition of R, the previous, or in the statement of the theorem, this means that R here is the collection of all pairwise disjoint union of elements in the semi-ring H. Therefore, R is a semi-ring that contains H. Hence, this proves our claim, and therefore we have this inclusion. And as we said, when combined to this inclusion here, we therefore conclude that R is equal to the ring generated by H. Okay. Again, to summarize this theorem, so how do we generate the ring with a given semi-ring? We just need to take the pairwise disjoint union of elements in the semi-ring. That's the proof. Okay, in the next lecture, we will discuss Lincoln systems.